فرصه سعيده جدا يعني ان احنا نكون مع بعض هنا. يمكن الموضوع اللي انا هتكلم عليه شويه ممكن يكون خارج عن المألوف عن مجتمعنا العربي وعن التلقين في العلوم. ده هيكون موضوع الحقيقه يعني شامل حاجات كتيره، يمكن يكون will be very intriguing ان انت تقدر تعرف يعني very early detections لحاجات كتيره جدا. الموضوع ده هيكون ضامن معاه حاجات في الكوانتم ميكانكس، في البايوميديسن، في البايوسنسورز، في حاجات كتيره جدا خاصه بالسنسيتيفيتي. تمام. هيكون في بعض الوصولات بين الناتشرال ساينسز والانجينيرنج، واي ثينك ان هنا حضراتكم اكيد كلكم جايين من باك جراوندز من العلوم او العلوم الهندسيه. كده في الاخر هتقول الى الناتشرال ساينسز، الكيمستري، الفيزيكس، الماثماتكس، كل ده يعتبر البيزك مايلستون للعلوم المتقدمه. اسمحوا لي اقدم باللغه الانجليزيه لان اكيد حضراتكم عارفين العلم اللغه الاولى بتاعته هي الانجليزي، فاتمنى حضراتكم cope with English. First of all, I want to welcome my professors, Dr. Ibrahim Shirbini and Dr. Omar, Dr. Tamer. It's a very great moment for me to represent in this Al-Adam. I'll be talking about metallic nanoparticles and polymeric nanoparticles or nanostructures-based sensors. I want to ask, first of all, I want to ask you a question. I think that you all here can doubt or undoubt that we use sensors in our everyday lives. Can anyone here doubt about this fact? No doubt. Okay, this is great, because if so, you wouldn't have been able to hear me. Actually, my voice is like is a sound wave, and the sound wave is transmitted to your eye, your pinna, and then your pinna collects the sound waves to try to transduce the sound waves to the ossicles inside your ear, and then the ossicles vibrate to get signals to the cochlea and the fluid of the cochlea, then to information processing in the brain. This is very I know this is very quick, but I want to let you know that there's no fact that this is a sense. Okay, this is a sense. So when I talk about sensors, there are two classifications: artificial sensors, which I'm going to talk about in details, that we're trying to imitate the natural sensors or the natural senses, which are five. I will let you know. Let's begin up. Start off by the environment. The two difference between the natural sensors and the artificial sensors, as you can see, is not much like something, the terminologies. As you can see, instead of nerves, we have analog circuits for wires. Okay? The environment will be such the beginning of getting signals, of getting sound waves like our ears, and we can say also the lights for our sights. And as you can see, the signal conversion from, as I told you, we convert the sound waves to signals, to electrical signals, to be translated in our brains, and then you understand me. I think that you all here feel something toward my presentation, whether it's amazing or not. This is a sense. Okay, this is a chemical sense. We have two classifications of senses, which are chemical phenomena and physical phenomena. We have chemical phenomena, which are tasting and smelling, depending on the chemical reaction. Tasting, our tongue, our smelling, our nose. I'll be talking about very, very interesting application in nanosensors for early detection of cancers by electronic noise. This is very, very amazing. I will let you know at the end of the presentation. This is our friend Martin by his five senses: tasting, hearing, sight, smelling, and touching. This is the brain, the classifications of the senses in our brain. And I think that you all here may hear something from the our traditions that do not let anyone to hit you in this part of your head, because this is connected to the vision, as you can see, and this is connected directly to the antenna of our eyes, or the retina of our eyes. And let's begin up by sensors, artificial sensors. We're trying to imitate our natural sensors. As I told you, this some classification. We don't have to go inside the depth of every sensor of this, but I let you know that this first one is called electrochemical sensor, and this is, as you can see, the cantilever sensor for electromechanical detection, and the acoustic wave. This is a very intriguing sensor, and the electrochemical sensors for detection of gases, for toxins in the liquid phase. Well, there's some parameters. I'll not talk about much of this. It's not my central focus. Some parameters should be provided in fabricating and manufacturing sensors, like the selectivity, the linearity, limit of detection, quantitation, limit of quantitation, response time, dynamic range, selectivity, accuracy, precision, is not to elaborate each one of them, but you have to know that these are very intriguing and very important parameters for fabricating sensors. Okay, this is some parts of the parameters. As I told you, there are noises in sensors. If anyone here have a background in sensors, we have limits of noise which we should get rid of, or should get the deviation which occurs between the signal which you want to detect and the noise. Okay, this is not only important, and also the hysteresis. There is a problem only know about hysteresis detection of two signals that are opposite to each other. Well, okay, I talk about nano. Imagine with me, I'm talking to you, and you see me, and inside, beside all of us, we can see a virus. We can see a glucose. Welcome to the nano land. Yes, when we are talking about nano, why are we talking about nano? Nano is very interesting field, and very multidisciplinary fields that connects all fields, all of science fields together. We have to know that we should get rid of basic or traditional sciences, or like, I cannot say electrical engineering, I cannot say biomedicine. We have to collect them together, as I will show you the connection between molecular electronics and biomedicine. This physics, chemistry, medicine, all of them. Okay, this is the metric scale, as you can see. Welcome to the nano. All right, so, okay, there we have nanomaterials. We have to get some basic idea about nanomaterials. We have clusters. If you hear about quantum dots, zero-dimensional nanoparticles, we have quantum wires, which are called nanowires, fibers, nanorods, nanotubes, carbon nanotubes. We have also nanotextured surfaces, which are films and coats, as you can see. This is the dimensionality. It's called zero-dimensional one. Okay. The third one is bulk nanocomposites, or also you can say crystalline. There are some classifications. We have crystalline, we have crystallized, we have amorphous. Okay, these are taken from papers. Nanocomposite, this is super lattice films, nanotextured or thin films together, and this is a nanotube. As you can see, that's taken from TEM, transmission electron microscopy. And unfortunately, I have to tell you that I was thinking to get with me some gold nanoparticles or silver nanoparticles, but there was a problem in this area. And as you can see, this is the macro scale of silver, of gold, the macro scale of gold. So let me tell you something about the next slide, which is very intriguing. When you say gold nanoparticles by red color, yes, we have to mention something very intriguing in nanoscale or nanotechnology, that we have different properties that are very amazing when you think that something like optical properties, as you can see, electrical properties are going to be very different. Optothermal properties, we have luminescence, absorbance, like reflectance of light. Those are very different from the macro scale level, and from what we already know about our material, ordinary material. Okay. All right, this is taken from Indian Institute of Technology. These are some gold nanoparticles. This mission, this slide is something related to seed-mediated growth. What the meaning of it? Do not focus on the terminology. I want to tell you that we have to mention some of different shapes of gold nanoparticles. For example, of nanomaterials in general, those are some classifications of the shapes. As you can see, we have nanorods, we have spheres, we have nano particles, we have bulk, like we have cube, like, and whatever. Okay. This is taken from a very important research. As I told you, we have completely different properties. This is a gold nano rod, or gold nano thin film, nanofilm. This is a very intriguing when you see. This is the first one. We get it into this is taken from TEM, transmission electron microscopy in the nanoscale, and we have to see that this is the first. I'm trying to compress the nanofilm between two electrodes, or between two, like say electrodes, source and the drain. I'll be also talking about semiconductors. You will find that when we get it successfully, we'll find that I can compress it and it can be retained again to its original size. So we have mechanical properties. We have very important mechanical properties. They can be used in many applications. What I want to tell you that we have completely different properties from micro scale level to nano scale level. All right. Okay, well, just to talk about carbon nanotubes, I'm not so focused on how we can manufacture them. I will tell you that the most important things that we can manufacture, top-down approach for manufacturing nanomaterials and bottom-up approach. You can get for top-down like lithography, electrochemical TIB, focused ion beam, and for bottom-up we have something like chemical vapor deposition. We have self-assembly process, and this is very important when you see that we have different shapes of nanocarbons or carbon nanotubes. This is the first one called bulk ministry fullerene, and this is an armature, or this is three classifications of nanocarbons or carbon nanotubes. We have armature, something called chiral, something called zigzag. This is according to a mathematical equation. I can write it, but I have no time for that. I can tell you that this is very intriguing, as I told you in the beginning. This is a mixture, a super lattice of sciences together. Okay, let me just focus on the applications. This is some properties and some characteristics for the carbon nanotubes. As you can see, we have thermal conductivity, we have elasticity, as I will tell you. So compare between carbon nanotube and diamonds and copper, aluminum, iron. We're going to find this is very, very amazing when we see that it's 3,000 watt per Kelvin. This is something cannot be measured. I do not want to focus on how, because this is a tall topic. I want to focus on the applications. As I told you, it's excellent elasticity of carbon nanotubes. We can compress the nanotube by a tip, and when releasing the tap, we're going to find the same original size. Wow, this is amazing. Okay, this is an application for NEMS, nano electromechanical systems, or nano-mechanical sensors based carbon nanotubes. This is a cantilever between two electrodes. We have cantilever for detection. You can imagine I will detect a proton mass. Wow, reactogram, 10 power minus 24 gram detection. Detection of something that's very, very, not very, it's very, very, very small. Even smaller than the femtosecond, as we know. Okay, I'll let you know that this is when we manufacture carbon nanotube with specific shape. The diagram here just gives you the frequency of the detection. There's some fluctuations on this cantilever or this mechanical system, because we have, and since we have to improve this, you cannot imagine that this is only detection here or detection here, and then by annealing, by passing electrical currents between the two electrodes and the drain, we can get annealed diagram that when we look at here, we will find that this is a detection for something, but if we have a certain peak, but very raised certain peak, we will be sure that this is something has been detected. Okay. Also, yes, we have, as I told you, in biomedical sciences, we have applications in drug delivery. We can encapsulate nanoparticles to target it into the cells. It has no damage for, does not cause any damage for the cells. Can pass through the cells very with very good facilities. And we have to measure something without any cytotoxicity or toxicity. I'm not to remember. It's called toxins. If you know toxic materials, cytotoxicity is like something anti-toxic. Okay. Cancer cells, for example, we can target a drug for the cells. We can encapsulate it, as you can see. This is gold nanoparticles encapsulated by specific lesions. Lesions according to their structure, with the polymer, with any kinds of capital lesions. Okay. We can also, yes, I'll be also talking about this in details. I will let you know from this slide that we have applications for imaging for cancer therapeutics, and I will tell you a little bit from our research. Those are all researchers taken from very recent researches in science. I will let you know something about Dr. Mustafa Said. I'm sure that you all hear about it. I will tell a little bit of his research. You're really lucky for meeting with him here. And this is also applications for drug delivery, or sorry, gene delivery. We can encapsulate a gene, specific gene, with fluorescence. As I told you, when we get into nano, we get fluorescence, we get imaging, we get very optical, very important optical properties, very intriguing electrical properties, and others. Okay, I want to wrap it up because I have a lot of things to tell you. This is a detection for DNA. Also, we have to mention that we can get it from the diagram when we shift a peak, as you can see. This shifted peak refers to a detection, a specific detection from whether you can just focus on 50 wavelength to around 70. This is the wavelength of visible light. Okay, I want to wrap it up. Quantum dots based biosensors. Quantum dots are classifications of semiconductor and nano. This imaging for rats. Here by biological reasons, you can tell if we use quantum dots for imaging, quantum dots for cancer detection. This is the paper of Dr. Mustafa Said. I will not focus on the details. I will let you know that we have infrared light that can be affecting the nanoparticles. We can target nanoparticles, hold nanoparticles to the cancer cells. Fortunately, when we expose infrared light, we have completely different properties, optical properties. There's some radiations that get from nanomaterials that are going into details how, but this is how we can get rid of cancer cells. This is very early stages of detection, of cancer diseases, getting rid of cancer cells. We have some disadvantages, and this is very early stages to apply. Sometimes we can ask ourselves, after dying, after the death of the cancer cells, where gold nanoparticles go to. Okay, wrapped up. This is carbon nanotubes based field effect transistor. I'd like to mention what's the transistor, but believe me, we have we can get molecular modification of the carbon nanotubes, for example, or silicon semiconducting silicon nanowires. In between the source and the drain, we have currents that go from a point to another point. If something is detected, I will let you show you within this time. If any detection occurs, we have to let this diagram is going to be different from the ideal case. I'm going to wrap it up quickly. Electronic skins, okay. Electronic skins, this is very important when you see, for example, you have you have a cardiovascular problem in your body. This is going to be very amazing when you have something like electronic skins that can be connected to wireless and then connected to policeman, to clinician, to doctor. Wow. You can just imagine with me, I have a problem now, I attach something called electronic skin. The electronic skin can be fabricated by into nanoscale. Okay, can be put in my the area of my heart, and if there's a problem, it will be detected. There will be an emitting signals to the policeman, to the clinician, to my doctor, and it's going to contact me immediately. Okay, this intervention of them into my state. Also, there are some prosthetics problems. Anyone has looked at it. Okay, I will wrap it up. Okay, this is what I'm focusing. This is my field of area, my field of area and research. This is electronic noses for early detection of cancer. I will wrap it up. First, I will begin by optoelectronic nose. We have optoelectronic nose that can detect different gases, toxins, radioactive gases by a specific pattern. We have chemical reaction. Via this chemical reaction, we can get signal. This is the imitation. What I want to let you know when you get out of here, that we have to imitate our senses in the nanoscale. When we imitate our senses in the nanoscale, this is the device called electronic nose based field effect transistor. We can get this is a genius. This was not considered by anybody in the world 2 years ago from a genius professor. He used specific nanos, called nanos. I will show you the device here, based field effect transistor. Any signal that go from a source to the drain, okay, and there's unordinary or something unusual in the detection, there will be such a peaks. Like, I want to show you if I have time. I don't have time. A video taken from Harvard research, from the original researchers in Harvard. I got it yesterday. And we have to know something was not considered, that the cancer cells emit VOCs called volatile organic compounds. The volatile organic compounds like hexane, like ethanol, like some chemical compounds that can be detected via encapsulation and molecular modification in the nanowire. The nanowire, this SINU silicon nanowire, is molecularly modified by specific compounds that can be detecting those volatile organic compounds, and we choose these compounds specifically because they can be very sensitive towards those gases. This is called selective sensing. When we want to detect one thing, we select the selective sensing. When we want to detect multiple gases or multiple volatile organic compounds, we have to get cross-reactive sensing. For example, I want to detect S1, S2, S3. Okay? There will be such a diagram that shows me this is S1, this is S2, this is S3, as you can see. This is cross-reactive sensing for multiple detections of various gases or various toxins and herbs. This is the detection process. And this can show you that you have a cancer, malignant type cancer, stage 1. If I have time, I could elaborate for you from a fundamental point of view via quantum mechanics and molecular biology, also in addition to microelectronics and other types of science. This is very multidisciplinary as I said. This is the first version of nanos, but after some modifications and development, we have only this system. Okay. This is the detection of cancer via the smelling cancer, or sniffing out cancer. Okay. This is the first, as I told you, and then we use our minor sources. Thank you.